Let's talk about symmetry. The average human is symmetric about an axis that passes through the middle of their bodies, from the top of their head down through the center of their torso. Now, it would be a weird thing to see if humans were symmetric about an axis that passes through the center of their torso. We don't have this kind of symmetry. Now, you're familiar with symmetry because every time you look in the mirror, you see a mirror reflection of yourself. That reflection shares the symmetry of your body. Symmetry is actually a very important part of physics, and as we're learning about Gauss's law and electric fields, having a good understanding of what is symmetric and what isn't can vastly simplify your calculations. In fact, let's talk about one type of symmetry that you'll see pretty frequently: cylindrical symmetry. Well, let's take a very long cylinder. Imagine you're standing on this cylinder and you are just walking down the cylinder from the left to the right. Well, the cylinder is so long, everything is going to look the same. This type of symmetry is symmetric about an axis that passes through the cylinder. So we'll call this translational symmetry. No matter how far you walk, the cylinder looks the same. This is one property about objects that have cylindrical symmetry. Let's take our same cylinder. But this time, let's look at a plane that passes right through the center of the cylinder down the middle. And let's say this time we are standing on top of this cylinder. Well, if we walk around the cylinder, everything is going to look the same. So we could say that this cylinder is symmetric with rotation about some axis. That's another property of cylinders, that they are rotationally symmetric. No matter how much you rotate the cylinder or how little you rotate it, everything about that cylinder will look the same. The symmetry of an object will match the symmetry of the electric field. So let's see what we mean by a symmetric electric field for the case of something with cylindrical symmetry. Let's take a very long wire. Now, this very long wire, we could say, is cylindrically symmetric. Now, this wire is so long that any object on top of it, that wire would seem to be infinitely long. It is so long. Well, let's take an axis that passes somewhere through this wire. Now, because this wire is so long, let's take an axis that passes through this wire. Because this wire is so long, it doesn't matter where we place the axis. The wire, for all intents and purposes, can be modeled as an infinitely long wire. Well, let's take a very small element of this wire. And actually, before we do that, let's say this wire is full of electric charge. For simplicity, let's say that this is a uniformly charged, infinitely long wire. Well, let's look at an electric field for a representative element of this very long wire. And let's take this electric field, let's look at a point right here and see what the electric field is for that point. I'm going to change the color of this central axis. We'll just make it blue. If we pick a representative charge element, let's say we pick a charge element that is right here. And we look at the electric field at the point that I will label point A. We know that the electric field the electric field will be in a line directed straight away from the representative charge element. So if this is a tiny bit of charge, which I'll call dq, then this is a tiny bit of electric field. But remember, cylinders are symmetric about any axis that passes through its middle if the cylinder is long enough. So in this case, the cylinder is infinitely long. So what this means is this cylinder has symmetry about this middle axis. And so that charge element on the left has a corresponding charge element on the right that also contributes to the electric field. And you know what? Those two electric fields, their x components will cancel. Let's go ahead and define our coordinate system since I just said x component. We'll do the x component along the length of the cylinder, along the length of the wire, and the y component parallel to that axis I drew. We could see from here that the x components of the electric fields, due to those tiny bits of charge, will cancel. They are equal in magnitude and opposite in direction. The components of their electric fields that don't cancel are the components that's parallel to that middle axis. Now we could even take a point below this line of charge, a point down there. Now that point down there will also have an electric field contribution from the charge element on the right and a contribution from the charge element on the left that is the mirror element to the one on the right. Due to symmetry, the x components, again, of these electric fields will cancel, leaving us with only a y component. And in fact, no matter where you go, no matter which axis you choose passing through this very long line of charge, since the charge is so long, the x component of any pair of charges will always cancel. Let's do two more. Let's do a component here. This one is farther away, so the electric field will be weaker. But there is a corresponding elemental charge on the other side. And once again, the x components will cancel, leaving us with a y component. If you continue this analysis for all of the points surrounding this wire, you would end up with an electric field that only has a y component. And this electric field is pointing radially away from the central axis of the wire. Now, we're idealizing this wire. We're saying it is infinitely long. And the reason why that's a useful approximation, a useful thing to consider, it's because for an infinitely long wire, the electric field is radial. Because of that, the electric field everywhere around the wire is pointing radially away from the wire. For example, if we took a point in which we are looking end on to the wire, from that vantage point, we would see that the electric field is cylindrically symmetric about the wire, pointing radially away. Now, that symmetry can be expressed by just drawing an imaginary surface that's a cylinder in which the wire is centered down the central axis of our imaginary surface. This imaginary surface in space we're going to call a Gaussian surface. Now, a Gaussian surface doesn't have to be a real surface. It doesn't have to exist physically in space. It is a mathematical surface that can be described mathematically. Now, from this vantage point you see here, that our electric field is symmetric everywhere around that cylinder. At every point on the cylinder, the value of the electric field is the same. It has the same magnitude, and relative to that point, it has the same direction because it is perpendicular to the surface of this Gaussian cylinder. Now, if we look at it from this vantage point, this cylinder has a length and it has a radius. And so now you can see why we say that this wire has cylindrical symmetry, because if we take a cylinder surrounding it, the electric field shares that same cylindrical symmetry. So we could say that long wires have cylindrical symmetry. Because the electric field, due to a long line of charge, points radially away from that long line of charge. Now, you might notice that I'm drawing the electric field lines more in the middle of this long line of charge, not so much at the end. The reason why is this long line of charge, even though it's long, it has a finite length. Because of its finite length, the ends of this long line of charge won't necessarily be radially away from the axis that lies parallel and on top of this line of charge. If we take, let's say, a point on the right side of this charge, let's take an axis on the right side of this charge, near the right end. And let's look at a point near that axis that we drew. That point right there, the electric field is going to have an x component. Now, you might be wondering, well, how is it going to have an x component? Well, think about it like this. To the left of that axis, there is all of this charge right here. All of this charge on the left will be contributing to an electric field. So I'll just do a couple of representative electric field vectors. Here is one from the left end. I drew kind of small because we're far away. Here is one from the middle. I'm going to draw this electric field vector a little bit bigger because we're closer. Here is one closer to the line of charge, or closer to the axis. Here is one right next to the axis. Well, now let's look at the contribution on the opposite side of that long line of charge. So that's basically the right end of this line of charge. And this right end might have a pretty strong electric field, and its contribution might have a mirror element on the left side. These two pieces are mirror elements. But notice, none of the rest of this line of charge has a mirror on the right side. Because it doesn't have a mirror on the right side, it is technically not symmetric with reflection. And that's because this line of charge has a finite length. And notice then that even though the x component of this end on the right, even though the x component gets canceled by the x component of its mirror on the opposite side, the x component of all of those other charge elements don't get canceled. So because those x components of the electric field don't get canceled at a point near to the end of this wire, this finite wire technically is not cylindrically symmetric, at least not at the ends. But if you're far enough away from the end, then to you, for all intents and purposes, the electric field will be symmetric. Because if this is a long line of charge, and this is what we're going to mean when we say long line of charge. In essence, when a point in space is relatively close to the line of charge, then to that point, that charge looks very, very, very long. So if we are far enough from the edges, the cylinder has, or this line of charge has cylindrical symmetry, which means that the electric field has cylindrical symmetry. And we could see that cylindrical symmetry by drawing a Gaussian cylinder about that line of charge. And the electric field at every point on that Gaussian cylinder looks exactly the same as every other point. So let's observe that cylindrical symmetry. Let's observe our Gaussian cylinder by looking from one end of the charge. if we are looking from that end of the charge, then what we would see is the wire, and we would see that the electric field points radially away from that very long wire. And notice, based off of how we are drawing this electric field, you could see that the electric field is weakening with distance, but it is radial. And we could say that this electric field is cylindrically symmetric because when we create our Gaussian cylinder about the wire, where the wire passes through the central axis of our imaginary Gaussian cylinder, well, notice that at every point on this Gaussian cylinder, the electric field looks the same as every other point. At this point on the right, the electric field is perpendicular to the cylinder and is of a certain magnitude. This point on top, the electric field is still perpendicular to the cylinder and has the same magnitude. This point in the lower diagonal, the electric field is perpendicular to the cylinder and the same magnitude as all the other points. So we could say the electric field has cylindrical symmetry, and that's a useful thing to be aware of, that the symmetry of an electric field will match the symmetry of the charge that produces it, if a symmetry exists. Well, let's take a look at another symmetry. Let's look at a point charge. So here's a point charge, a positive charge. You know that for point charges, the electric field points radially away from a point charge. And as I'm drawing this on this screen, it's looking very two-dimensional because I'm drawing on a two-dimensional surface. But if you could imagine that if you could imagine that all of these electric field vectors not only are pointing in the plane of the screen, but it's coming out of the screen, it's going into the screen. So it's pointing radially away from all vantage points. Well, that must mean that the electric field is spherically symmetric. Well, what do we mean by spherical symmetry? Well, let's take a look at a sphere. Here's our sphere. Let's say you are standing near an axis that passes right through one part of this sphere. And let's say now that you rotate this sphere about that axis. Well, if you're standing out here in space looking at the sphere rotate, the sphere is totally indistinguishable. Every part of the sphere is indistinguishable from every other part. The only way we even know that the sphere is rotating it's because someone is standing here near the axis, rotating around it, probably getting really dizzy. Without that person there, though, you would have no idea that the sphere was rotating because every portion of the sphere looks the same as every other portion. Now, you could even change your perspective. Let's say we're looking up on the sphere from down below. The sphere looks the same. We could even switch the axis of rotation. We could choose an axis of rotation that passes through the middle of the sphere. The sphere looks the same as it rotates. We could even choose an axis of rotation along a diagonal. The sphere will look the same as it rotates about that axis. So this is a nature of something that has spherical symmetry. Now, what if we take a plane and slice the cylinder, or slice the sphere? We'll take the same sphere, but let's take a very long plane that slices the sphere right through the middle. Well, the top part of the sphere still looks the same as the bottom part of the sphere. In fact, both halves look like a reflection of each other. So spheres are symmetric about a plane that passes through their middle along a radius. This is the nature of spherical symmetry. Well, if we then place our charge inside that sphere, notice that the electric field also has spherical symmetry. Because no matter where you are on the surface of the sphere, and let's call this sphere now, let's call it a Gaussian sphere. This is another Gaussian surface. And again, remember, Gaussian surfaces don't have to be physical surfaces. They are mathematical surfaces. So this Gaussian sphere that completely surrounds our charge, if we place the charge right at the center of the sphere, the electric field at all points on this sphere will look the same. At this point on the right, the electric field is perpendicular to the surface of the sphere and has a certain magnitude. Well, this point on the diagonal, the electric field is still perpendicular to the sphere and it has the same magnitude. At the point on top, the electric field is still perpendicular to the plane, to the surface of the sphere, and it's the same magnitude. And in fact, everywhere you go as you walk around the sphere, the electric field will have the same magnitude and relative to the sphere at that point, the same direction. That direction being the direction of a vector normal to the surface of the sphere. So point charges have electric fields that are spherically symmetric. Also, spheres of charge, spheres of uniform charge also have an electric field that is spherically symmetric because, well, if we have a sphere of charge where the charge is distributed uniformly about the sphere, well, that sphere, the geometry of the sphere, since the sphere has spherical symmetry, the geometry of the sphere, the electric field will match in symmetry. So that means for spheres even, the electric field generated by that sphere is going to be spherically symmetric. Let's now look at a plane of charge. A plane of charge isn't all too much different than a very long line of charge. So here is a plane, a two-dimensional plane in space. And let's say this plane is a collection of charges. We will say the charges are uniformly distributed across the surface of this plane. And let's say this plane is so big that it is infinitely large. Well, if this plane is infinitely large, then the electric field is going to have what we call planar symmetry. So for example, let's take a point hovering right above the middle of this plane. Now, even that word middle doesn't have meaning if the plane is infinitely big. There is no middle if it's infinitely big. However, because I'm drawing a representation of this plane on this finite page, I'm going to say, I'm drawing it from the middle. But for all intents and purposes, we will say that this point is so close to the plane in connection to the size of the plane. According to that point, the plane is going to seem very, very big, if not infinite. So I'm going to draw it from the middle to kind of help remind me that this is a very long plane of charge. Now, for this very long plane of charge, we could see, similar to a line of charge, there is always going to be a mirror charge on both sides of this axis on which the point in space lies. For example, if I take a point right here, this point will have an electric field contribution, but there is a mirror charge on the other side that also contributes to the net electric field at the point I drew. And the horizontal components of these electric fields will cancel because of that symmetry about that line through which on which that point lies. Now, I could take a point right here, and the electric field contribution to that point will be coming slightly at us. But then there is a counterpart point on the other side. And the electric field contribution of those are going to have a horizontal component that will cancel. I could even take a point farther away. Let's take this point right here off at some angle. I'm going to draw the electric field vector a little smaller because it's farther away. But that point over there has a mirror on the other side. And the x component of the horizontal component of the electric field will cancel. Now, even though all the horizontal components of the electric field cancels, notice the vertical components do not. The vertical components sum together, such that at that point, there is going to be a net electric field that is vertical. And in fact, since this plane is so big, it's essentially infinitely big, the electric field will be the same magnitude anywhere along a line that's a certain distance away from the plane. Well, you know what? Again, this plane is so big that actually the electric field is going to be uniform due to this very long plane of charge. And not only on the top of this charge do we have an electric field, but let's not forget underneath as well. The electric field matches the symmetry of this plane. This plane has what we call planar symmetry. Well, let's look at planar symmetry. Let's take a very long plane, infinitely long. Well, if it's a very long plane, the plane looks identical whether you're at this point of the plane or here or here. So as you walk along the plane, everything looks the same. As you move along the plane looks the same. One part of the plane is indistinguishable from another part. So one property of planar symmetry is that everything looks the same with translation. Now, what if we ended up on the bottom of the plane? So let's look. Well, below the plane looks just like it does above the plane. So with reflection about the surface of the plane, you also have planar symmetry. You also have reflective symmetry, which is a property of planar blah. So you can see here that planes are symmetric about since both sides of this plane look the same, the plane is symmetric about its surface. So going back to the electric field, notice if we were on the surface of this plane and we were walking along, the electric field looks the same everywhere because the electric field symmetry matches the symmetry of the charge configuration that produces it. If the plane has planar symmetry and the plane is infinitely big, the electric field will have planar symmetry. If we flipped to the other side of the plane, notice how the electric field looks exactly the same as when we're on top of the plane. That's a property of planar symmetry. So another way of visualizing planar symmetry is to look at a Gaussian box. So let's draw our plane again. We'll draw electric field lines on top of the plane and electric field lines below the plane. This is going to sound weird, but let's take a cylindrical box. So our Gaussian surface that is a box, it doesn't have to be a cylindrical box, but I'm going to choose this as an example, and then I'll show you a rectangular box. So if we have a box formed in the shape of a cylinder, notice how the electric field looks exactly the same whether we are on the top surface of the box or the bottom surface of the box. If we were standing right here on the box, notice how the electric field is perpendicular to the top surface and it has a certain magnitude. Well, if we are standing right here at the bottom of the box, notice how the electric field is also perpendicular to the bottom surface and the same magnitude as on top of the box. You know what? The box doesn't even have to be centered on the plane for the electric field to have planar symmetry, because the thing about the planar symmetry is the electric field is uniform. It extends at constant magnitude in the same direction forever. So even if we are way down here, the electric field is still perpendicular to that bottom surface, has the same magnitude. Now, if you're standing right here on the box, that's a different surface. But relative to that surface, notice that if you were to, let's say, walk around that little cylinder we drew, the electric field will look the same to you as we walk around. This electric field on the left end at this point is going down, and it's a certain magnitude. The electric field on the right end as we walk around is still going down, and it's a certain magnitude relative to the surface of the sphere. So this is what planar symmetry means. For us, planes of charge have planar symmetry, and what that's going to mean is the electric field is uniform. It is constant in magnitude and in direction. Now, I mentioned that I took a cylindrical box here because that's what I'll often do when I'm problem solving, because I'm dealing with three surfaces that actually make up my one Gaussian cylindrical box. Now, you might be wondering, well, why didn't you choose like a rectangular box? Well, let's take a look here. So let's draw one. I have to draw more things. So that takes a little bit of time. That's not the real reason, though. Notice this box has 6 surfaces you have to look at. So there's the top surface, the bottom surface, right side, left side, front, and back. While the Gaussian surface has only 3 sides to deal with: a top, a bottom, and a side. So one, I have half as many sides to deal with. And you might be thinking, well, why does that matter? Well, I'm thinking ahead here. We're going to use Gaussian surfaces to help us determine the electric flux through surfaces, through closed surfaces that have some form of symmetry. To do that, we are going to use Gauss's law, because Gauss's law says that for closed surfaces, that the electric flux through a closed surface is directly proportional to the amount of charge contained within the surface. And as you'll see, calculating this surface integral is going to be a sum of integrals over each surface. If I have 6 surfaces that make up a Gaussian box versus 3 surfaces that make up a Gaussian box, then that would mean I would need to have 6 integrals for the Gaussian box versus 3 for the cylindrical box. You'll see this more in a later video.